think everyone there is damn tough.
Yeah. You're going to get yeah.
Really careful with it.
Oh, there. Oh, what do you say? What do you say?
Okay, come, let's begin our lesson today. Together we had about 5 minutes earlier. Okay, so this is a brief recap of whatever we've gone through so far. And today we're finish up the last part basically. Okay, so we went through electron reflection, that's like the main concept covered. Okay. Second thing we went through is the new way of doing electronic configurations. We use this thing called the SPTM notation. Okay, you can like briefly look through. Okay. We also looked at the structure of an atom. So remember, an atom, right, the main structure that I'm going to take a look is this hierarchy. First of all, we have the quantum shell. You can think of the quantum shell as like the boss. Okay, he's the biggest guy. But then clearly, right, okay, it is too much. Okay, we still need to zoom in to the hierarchy. After a quantum shell, we call it a subshell. The subshell is like their managers. And then finally, okay, under the managers, there are a few workers, right? It's like the workers. So this hierarchy must be used when we discuss your thing. Okay, later we'll discuss all this. You must be very clear with the terms, okay? Because some people just throw these terms however they like. And when that happens, right, you're just gonna get questions wrong. Okay, so that's the structure of an atom. Then the last part of this topic is, which is still ongoing, is this periodic trends. Basically, how do you navigate a periodic table? Okay, guys, you all remember last week we went through down the. And again, since there's a lot of explanations, it is very difficult for us to like kind of memorize everything. In fact, I do not want anyone to memorize anything. Okay, you need to know what's the basis of your explanation. So that when you go down the group, what should we explain first? Can you all remember? What do we explain first so that we can use that to carve our way towards the answer? Okay, it's okay, this is the direction, but then guys, whenever you go down the group, you should always start off your answer with the number of quantum shells. Okay, this one is very easy. So it's very logical. This one don't need to memorize. Because guys, when you go down the group, what happens to the number of quantum shells? It always increases, and we can use this to explain a lot of different things. And what do I mean by a lot of different things? Okay, so most of we're basically going to focus on two different trends for this chapter. Atomic or ionic radius. Okay, so that's the sign of the atom / ion. So very easy one that we did last week is this. When you go down the group, what happens to the number of quantum shells? Increase. So what happens to the size of the atom? Obviously, increase, right? The more shells. Okay, so that one very simple. But okay, we also use that to explain ionization energy. So remember, ionization energy is the energy needed to remove an electron from the atom. I'll recap a little bit of IE with you guys. Okay, so you can just take a look first. Okay, but before I recap that, guys, take a look. When we go across a period, does the number of quantum shells change? No. So we can't recycle the same explanation. So today we're going to zoom in into this new idea called effective nuclear charge. New idea that you never really see in secondary school before. And this one, it looks cheap, right? But honestly, it isn't. Later we'll see how this works. Okay, but let's just recap ionization energy, what it's all about. Okay, it is the energy needed to remove an electron. Okay, remember, electrons are being attracted to the nucleus, so there's something holding them in place. You're supposed to use this energy to overcome these attractions. Okay, so remember, what is first ionization energy? What does this mean? You're removing which electron? Okay, first electron, right? Okay, so very simple, guys. When you remove the first electron, it's from the atom. Okay, so how do you write the equation here? Okay, let's just say X is an atom. You form what? X plus. Okay, you remove an electron, you're definitely going to get a cation ion, and then you balance it out with an electron. Now remember, this is the most important part. Later on, when we do some tutorial questions, you will see why this equation here will help us in a lot of scenarios. Okay, so remember, again, I can give you guys any example here. For example, if I were to give you guys ionization, how do we write down our equation? Okay, good. You are removing an electron from X3 plus in order to form X4 plus. Now the reason why is because you started off with a neutral atom. What's important here, guys? Do we look at the left species or the right species? Left. As highlighted in the last lesson, you must be focused on the left species. Why? Because you are removing the first electron from the X. No, you're not removing the first electron from the ion. Secondly, you are removing the fourth electron from the 3 plus PC. That's why I was always focused on the left hand side. This is important, okay, because a lot of people see 4 and then they think 4 plus. No, okay, you must minus 1 first. Okay, later there will be questions asking you on this. Okay, do not get it wrong. Okay, so that's a rough idea here. Now we're going to zoom in onto, I think we stopped off at page 24. As mentioned, down the group is easy. We'll go down the group, more shells. Okay, that one everyone can do. Okay, but now let's take a look at what's effective nuclear charge. Okay, basically, nuclear means nucleus, agree? So nuclear charge just means how attractive the nucleus is. It is not a formal definition or anything, it's just for you to understand. Okay, nuclear charge is just how attractive it can attract the electrons. Okay, so the thing is, there's the word effective. Effective just means overall. So I need you guys to take a look at this formula we're going to go over. For effective nuclear charge, I'm going to use Z effective. Z stands for nuclear charge. So effective nuclear charge means that symbol over there. Okay? The formula is this. Effective nuclear charge is nuclear charge minus this S over here called Curie effect. We'll need to use this formula not for calculations, but just to figure out the trends. Okay? Now guys, as I mentioned just now, Z is nuclear charge. What particle in the nucleus makes it able to attract electrons? The protons. Good. Okay, so guys, the more attractive the nucleus is, that means the more protons it has. Agree? So the nuclear charge, you must tell me about the number of protons. If the number of protons increase, very simple, your nuclear charge increases. How about your shielding effect? Okay, so it's about kind of like electrons. Okay, let's explain this. What is shielding? Shield means it's kind of like a obstruction, right? Okay, so let me explain this. Imagine the nucleus, and then I want you guys to imagine this as the outermost shell. Now, between the nucleus and the outermost shell, there are bound to be attractions, right? Now, the issue is there only the outermost shell? No. There is also a lot of inner shells, right? So imagine this, there is a shell inside, and this shell will effectively block these attractors. Think about it, okay? It's like when you have two magnets, you confirm got play magnets as a kid, then you put your hand in between the magnets. Confirm the attraction will be stronger or weaker? Weaker. It's the same idea over here. The inner shells will block the attractions. So guys, the shielding effect depends on this, the number of inner shell electrons. Okay, so it's like when you go for orientation, you start to see this guy, he looks very cute, right? Okay, or whatever. Okay, you see this guy over there, then you want to chase after him, you're attracted towards him. However, because he's so attractive, that means other girls are trying to go for him also, right? Okay, that's why all these are competitors. Imagine this, look at the inner shell over here. Imagine that there are so many competitors. What are the higher or lower? Definitely lower, right? So the attractions are going to get a lot weaker. So the more inner shell electrons you have, it will reduce the nuclear charge. It will make it harder for you to get to that attractions. Okay? So we will use this in a example later. Okay, so you can take a look at page. Let's answer this page, 24. Okay, let's do this. The question said atomic radius decreases across a period. Okay, you all must first tell me, across the period, what happens to the number of protons? Okay, good. Number of protons increase, so you can tell me nuclear charge also increases. Okay, so take note of that first. How about the shielding effect? Okay, right, let's furnish a little bit of why. Okay, as you go across the period, you're adding electrons to the inner or outer shell. Outer shell. So the inner shell basically stays the same. Okay, look at the phrasing here. Just now we say constant. That one's slightly wrong. You must tell me shielding effect remains approximately a bit longer. So you use the word relatively constant. Never say it's constant because there's no such thing as perfectly the same one. Okay, your choice of word is very important. So it remains relatively constant as the number of inner shell electrons the same. If you don't believe, you can also write down the electronic configuration, and you will notice that all the inner shells stay the same one. There's another way you can explain this. Okay, so I want to write both down. Okay, it remains relatively constant as electrons are added to the outer shell. Also, another way of conveying the idea that your shielding effect doesn't change much. Okay, up to you to choose. So guys, if your nuclear charge increases, shielding effect doesn't change, increases. Okay, good. So look at the formula, it will really help. So that's our final conclusion. You can see this is how it's integrated as quantum shell gradient. So effective nuclear charge increases. Okay, good. And again, guys, you must break down the idea of nuclear charge. Nuclear charge, let's say, is about attractions, right? So the attractions become stronger. But guys, it's attractions between what? Okay. Good. Okay, so as I mentioned just now, based on the diagram, it's the attractions between the nucleus and the valence electrons. It becomes stronger as well. In exam, unfortunately, I don't think you can use the arrows. You must write increases. Right? If you try to find it. Yeah, maybe if you run out of time, maybe like legit an exam full time, you can try. But I don't know whether the teacher will find out. How far okay, so attractions become stronger. So guys, what's the final thing to explain? Okay, you can just say atomic radius now. Okay, because if the attractions are stronger, right, it's going to pull the valence electrons closer to itself. So atomic radius decreases. You can clearly see the explanation here is much more elaborate compared to down the group. So if there's anything you really need to study, you'll be across the period. Down the group, kind of you can wing it yourself out. Okay, can. Now let's turn over to page 25. Okay, we explained atomic radius. Now ionic radius is pretty much the same trend. Okay, in the question, can you highlight the word generally? It's already underlined for you guys, but this is very important for later. Do you all have any guesses? What does generally mean? They could have just said it decreases, like just now. Okay, overall trend, yes, decreases. But in the middle, inside, it doesn't have to perfectly decrease, right? There could be some anomalies, kinks, right? Okay, so we'll explain that in a bit. Okay, but first of all, why does it generally? You all realize it's the exact same explanation. Okay, you're going across a period. What happens to the number of protons in those ions? Now, the number of protons, is it still increasing? Yes, actually. Guys, again, ions is different electrons, but not protons. Protons are still the same one. Okay, so when we, first point is the same, you can agree on that first. Okay, second point, okay, let's take a look at the configuration that you all can see. We are discussing two groups of ions. We have the K ions on the left side, and then the N ions on the right side. Can you just do me a favor and then just count in the K ions, how many electrons do these guys have? Al3 plus, Ag2 plus, and sodium plus. All 10 only, right? Okay, so you can write this down. All of them are 10 electrons. How about the N ions then? 8? No. Phosphorus, sulfur, and chlorine. 8? No, You look at the periodic table. That's a periodic table. So you must know the number of electrons. What's that book? Okay, so 18 electrons and 10 electrons. Guys, if all three of these guys have the same number of electrons, okay, let me introduce a new term. This is also known as, they are all isoelectronic. Isoelectronic just means same number of electrons. So across these two groups, they are isoelectronic. Not with across two groups, but within each. So just a new term. And guys, how does that relate to our shielding effect? If in each group they have the same number of electrons, that means the shielding effect also remains relatively constant, right? Okay, this one you don't even have to care about the shell. Why not? Because same number of electrons, inner, outer, all same. So the shielding effect confirm the same as well. So you see, first point and second point exactly the same. You can pretty much just copy and paste. It is a recycled explanation. Then of course afterwards, effective nuclear charge increase, attractions will also increase. So the ionic radius will also increase. So slowly go and process this information one more time. Okay, but that's the idea. You're recycling the same explanation. Having ions or atoms in both cases, okay, you will get the same result. Weakly. It's just weakly. I can't help but watching it wiggle. Imagine the guy sitting beside you in the exam, then he see that thing at the peripheral vision just slowly wiggling. So curious. But then when you look over, right, then it's like, oh,
The whole point is to, challenge people.
nice. Wow, the whole point is to bigger it yourself.
Yeah, man, same thing. But I hope I don't do it.
Okay, so this is only one part of ionic radius. Okay, the reason why we are still learning this part is because it does have a catch. Okay, and with that, I think it's that graph drawn on the next page. Okay, so once you're done with this, okay, you can go over to page 26. Okay, we have to sketch a graph. Right?
Oh, that will be pronounced.
Oh, the same graph. Okay. Oh,
Yes.
okay, before we draw any graph, okay, can you guys write down the configuration for 10 electrons and 18 electrons? Just put it under there first. Okay, you don't have to write for all 6 because it's only 2 different number of electrons. Okay, in the meantime, I will draw out the graph. Okay, so you can sketch out this graph also. Okay, we're gonna take a look at this. This is usually the part where you gain the additional mark. So this whole portion here of ionic radius is total 3 marks, including graph maybe. Yeah, okay. So maybe 1 mark for this whole explanation first, second mark for the graph, third mark for one additional part we're gonna go through. So you can see this whole part 1 mark, right? Okay, it's not because you need to write a lot. In JC, it's not about how much you write, it's about how easy it is to score that mark. And as you can see, it's easy to do this. Okay. Anyways, I told you guys to write down the configuration. For 10 electrons, it's 1s2, 2s2, 2p6. For 18 is until 3p6. Okay. Now the configuration will help us answer this question very easily. Just now, ionic radius generally decreases. Okay, I forgot to write that term. Yes, there's a decreasing trend across each group. But guys, if you take a look at the configuration between the cation and anion, what do you notice? What does the anion, what do the anions have? The cations do not. It has one more what kind of shell? Can you tell me the exact term here? Okay, it has this, yes, guys. Remember, quantum shell is the main shell, the delta, right? Okay, so it's one shell, two shells, three shells. That number over there represents the quantum shell. Guys, this is the bigger shell. So if you have an additional shell, that means the ionic radius of the n of those must be larger or smaller. Compared to chaos, must be larger. So when you draw the graph, guys, see there are a few features. Generally it decreases. So across the ions drops like this, agree? But then in the n ions, I need to see the decreasing trend, but higher. All three of them must be higher than the highest guy here. Okay, because that's the purpose of having an additional quantum shell. The shell is so big, right, to the point where it can surpass the entire cation's ionic radius. So yes, there's still a generally decreasing trend across each group, but between each group, no. Okay, so there's this very sharp increase. Now you notice I might have skipped silicon because sometimes the pattern does skip silicon, and it's fine. Okay. So you must get this, and next, okay, let's explain. Okay, why do anions have a much higher ionic radius? The anions have an additional quantum shell. Don't just tell me shell, because the examiner will be like, quantum shell or subshell, what are you talking about, right? Okay, the number 3 stands for quantum shell. Okay, thus, anions have a much larger ionic radius than cations. So let me just show you guys the mark allocation once more. I will do it with. You explain the general trend, this whole thing over here, up until here, 1 mark. The graph itself, probably another mark. Last but not least, to explain why there is an anomaly, final mark. Now, this is the most stingy allocation. Meaning to say they could give you more marks because you all just enter JC, they could be a bit nicer of you. Like let's just say this were to come out in a J2 paper. Yeah, it is this stingy. Sometimes even 2 marks. It can be that stingy. Okay, but no, okay, they'll give you a bit more chance now. You could get 4 marks from this. Like for example, the first part you might need to write a lot. So they might give you 2 marks. Then the graph drawing is 1 mark, then this one is another 1. Okay, so at most 3 to 4 marks, right? Okay, so this is one whole segment of 2 pages. Any questions so far? Okay, thanks. We're gonna move on. Okay, we still need to talk about ionization energy. And guys, pretty much, if you notice, okay, let's go through this again. Across a period, we need to talk about effective nuclear charge. So you think about this formula. Across a period, what happened to the number of protons? Increase. What happened to the shielding effect? Okay, so you notice I'm recycling explanations again. Hold on. Okay, before you all, I'll leave it to you guys to write. What happens to the effective nuclear charge? Okay, also increase, right? Now, when effective nuclear charge increase, then attractions also increase, right? But then afterwards, we need to talk about something. We cannot end off with ionic radius because it's not the answer. Right? What do we need to talk about? There's a final keyword. When it comes together with attractions. Yes, the attraction between nucleus and valence electrons much stronger. And now we are talking about removing these electrons. You need what to remove these electrons? You need energy, right? Okay, that's the idea here. Okay, the last keyword here is that I need to see the word energy. Energy needed to remove the first electron also increases. Yep, page 27. Okay, you need to edit your answer. So as I said, yes, we are writing a lot of things, but you realize that everything here is very, very overlapped, right? Okay, a lot of the things are the same. Okay, again, keywords. Okay, when you see the word attractions, they are all about energy as well. Okay, the rest is basically the formula. Okay. Okay, just seriously, make you all write this over and over again until it's really true in your head, right? Okay, because later tutorial questions, we will not do a question that requires the writing of this. It'll waste time, we do it in class. Later tutorial, we do the questions that you need to write. figure out. One of the questions we're going to do later is a bit math. Okay, like angle of deflection, there was a bit of math involved. So can be done, can be done. Later we'll do it, yeah. Okay, but it starts to get a bit interesting here under ionization energy. Okay, because again, I forgot to write about this. Energy needed to remove the first electron, again, generally increases. You see in the next page also. And the next page onwards, this one you actually need to pay closer attention to. Generally increasing means inside, when you scrutinize the trend, there's going to be some anomalies where it actually increases. So I'm going to introduce this called anomalies. Okay. When it comes to first ionization energy, there are two anomalies. And I need you guys, let me practice this first. You all need to so-called remember the the group numbers. Okay, it makes life a lot easier. Okay, from group 2 to 13, you will see a dip in ionization. From 15 to 16, you will also see another dip. Because as I mentioned, generally it will increase. So everything is usually going up, but from 2 to 13 it drops. 15 to 16 it drops, then continues going back up. It's good to memorize these numbers. Okay, but I'll come back to this later. Okay, so you can turn over to the next page. Okay, so on page 28, we're going to discuss the first dip in ionization energy. All right, so for this, okay, we're going to look at the group 2 element and the group 13 element, magnesium and aluminium. Can you quickly write down the electronic configuration? Okay, you need to write down the configuration sometimes if they ask you guys to. It's relevant to the question anyway. Okay, so high chance they can ask you to write it down. Right? Okay, so you should get this 1s2, 2s2, 2p6. By now you have 10 electrons, so now 3s2, 4. 1s2, 2s2, 2p6, then 3s2, 3p1. Okay? Now, what's important here is, guys, we are talking about first IE. Where are you removing the first electron from? From the respective elements. The first one is from which? In the 3s what? Quantum shell, 3s subshell, or 3s orbital? Subshell. Okay? Now, not 3s quantum shell, because S means we're talking about subshell already. So highlight it. From AL, we're removing it from the what? 3p subshell. Okay, I really need you all to get the terms right. Okay, so when we take a look at these two, just zoom in on these two subshells, right? What is the difference? Okay, they already tell you the answer. Aluminium is somehow easier to remove that electron than from 3s. Any idea why? There are actually two explanations here. We're going to cover both. Okay. Okay, so 3p is slightly further away, right? Okay, so that's why attractions are weaker, so energy needed is lower. Okay, this is one answer which I feel that it's very intuitive, but I slowly start to see it getting phased out. Never mind, it's still accepted. Okay, so let's write it down first. 3c subshell is slightly further away. Now don't write that further away because that one usually is for the quantum shell. The main shell is further away, but 3 subshell only slightly. So slightly further away from the nucleus. Okay, then the 3s subshell. That's why you all must use the correct terms. You all have one orbital over there wrong. And as a result, attractions between nucleus and valence electrons must specify are weaker. Which require less energy to overcome. So yeah, okay, so highlight these keywords once again. The second explanation is the preferred explanation, so I will show you guys what it's about also. And for that, I'm gonna talk a little bit more about subshells and the SPDF notation. Okay. So this is what's gonna happen. Here, we're gonna talk about an energy level. So I want you to imagine this. You've not really seen this before. It's fine. It's an energy level diagram. All the subshells you see over here have a certain amount of energy. Now it's actually quite simple because sometimes you might be asked for this. The 1s subshell is at the lowest energy. That's just how it looks first. Now, as you keep going further away from the nucleus, it's just going to increase in energy. Okay, so the next one, guys, is 2s. Make a guess over here. From 1s to 2s, is the jump in energy going to be very high or why? Correct. Good. Wait, wrong. Is the next 1 to 2 is the next quantum shell. Okay, so yeah, terms must be correct. Quantum shell is like the biggest jump already. So that's why the energy jump is going to be significantly higher. Now, next one is 2p. From 2s to 2p. Yes, it still increases. But that's why. Subshell. Can you see the idea now? Okay. You might need to plot this in an exam yourself. Okay, and it's not in the notes explicitly, but just take this down. Okay, so as you can see, smaller jump than next, which is big or small. A very large jump. Okay, so don't need to go and measure just to make sure it is approximate. Then PP also not very high. Okay, that's the idea. Okay, anything above that, right? You learn eventually. Okay, okay, but this is called an energy level diagram, and I want to teach you guys a concept that it's only taught in the later half of the year, but I think it's a very logical and simple concept. Guys, if you have low energy, are you stable or unstable? Logically speaking. Okay, actually it's stable. Okay, we write this down first. I'll explain why. If you have a lower energy level, it means you are more stable. If you have a higher energy level, it is less stable. As to why this makes sense, I want you all to think of it as like a little kid. I don't know whether you all go see and buy all those children, right? Very, very, very annoying. Okay, that's why I took one. Okay, but the idea is, imagine that kid is riding about making a lot of noise. He has a lot of energy, right? That little kid there, that little shit, right? Okay, it's not stable at all. He has a lot of energy. Just don't, yeah, okay, more likely fall out. That's good. Right, okay, but then you start crying. Okay, but then lower energy level, guys. If you have less energy, it's like the kid just woke up, so a bit tired, right? Okay, so that one is the easiest to control, very stable. Electrons are the same thing. Okay, electrons are lower versus higher energy level. This idea is very pervasive in the entire syllabus. Okay, so when we go on to a few more topics later, maybe in like May, right? We'll learn this thing called energetics, energy, right? Okay, so it all boils down to the idea. Okay, so take a look, guys. We want to go back to 3s versus 3p. Who has the higher energy level? 3p. Now, if you have a higher energy level, right, the electron is less stable. Is it easier or more difficult to remove this electron? Easier. Okay, if you can't understand why, come, let's go to the opposite end. You look at the electron in 1s, super close to the nucleus. Is it easy to remove an electron that's very close to the nucleus? No. Why? Because he has a very low energy level. He's very stable. Something that's very stable, do you think he wants to touch? No, it's like let's say like our dads, like our parents' generation. Okay, they like very tired all the time, right? Okay, you want to ask them go and do party and all that, they probably won't do it because they are very old, very stable already. They no energy to enjoy life. Right, okay, so that's the idea. Okay, 1s, you cannot remove the electron because very low energy. On the other hand, it has a much higher energy level as compared to 3s, so it's easier to remove the electron. Okay, so you think about it this way. This is the preferred explanation. The 3p subshell has higher energy level than the 3s subshell. And as a result, less energy is needed to remove it, it's easier. Okay, you don't even need to talk about attractions here, you can go straight to energy. Okay, less energy is needed to remove the 3p electron than the 3s electron. You will see variations of these answers. Your school notes, I will probably think it's going to be the second. Okay? So I introduce you all two ideas here. Idea of energy versus stability. And the SPDF notation is always going upwards. As for the gap, it increase the increased gap. Okay, it's dependent on quantum shell or subshell. See, so I hope this gives you a better idea of quantum versus subshell. Okay, any questions? Okay, so you just think of this, study the second one. I would prefer you all do it that way. Okay, again, we can move on to the next page, 29. We have another anomaly. And as I told you guys to remember, group 15 to 16, same thing, I want you guys to write down the electronic configuration. Phosphorus and I think sulfur, yes. Okay. Okay, at the start, you must follow this order. Eventually, you start to memorize the order. It's very best for everyone to get it. Not exactly lah. When it comes to energy level, right, it's just because the further you are from the nucleus, there's a high chance of you getting removed, right? Okay, you compare to 1s, 1s is super close to the nucleus. So this is the logic here. If 1s is super close, it has low energy level, so it's very, very stable. Why is it very stable? It's because it's very hard to remove him from his position. So he stays there. As compared to someone who's very far from the nucleus, like 3p. This guy, very easy to remove and get him out. So is he in a very stable position? No, not stable at all. Something that's not stable means it's full of energy. That's why the further you get from the nucleus, 1s2 all the way to 3p, it just increases in energy level because there's a higher and higher chance of you getting removed. Yeah, okay, so it's kind of like not very clear cut, but you just need to know, okay, as you go further out, energy level just increases. Yeah. In the first explanation only. The second explanation purely focuses on energy. You can add in attractions also, they won't knock you wrong. Yeah. Your higher energy level means you're further away, so the attractions are weaker. So can add in those. Okay. Configuration here. Okay, let's go through this. 15 electrons, 1s2, 2s2, 2p6, 3s2, 3p3. Then the next one is 3p4, right? Okay. So guys, where are you removing the electrons from? Okay, where are you removing? 3p subshell. Okay, so just highlight this out. Now the notes are okay. I think the instructions are not as good because they say draw the electronic box diagram for the outer quantum shell. Okay, guys, what is outer quantum shell in this context? So they want you to draw which ones? 3s and 3p, right? Because that's the quantum shell, it's the number 3. But it's not necessary, guys, because as we notice, you're only moving from the 3p subshell. You don't really care about 3s. So can we change the instructions over here? Okay, draw the electronic box diagram for the outer subshell or 3p subshell. Let's just specify. I mean, they're not wrong, the question is not wrong. It's just that you can improve on the instruction a little bit. And again, it's a good way of testing you guys your systems. Okay, can? Now, draw the electron box diagram very quickly. You know what's electron box? Okay, so never mind. It's actually just this. but in a pictorial format. Okay, so how does that work? Guys, how many boxes do I need to draw for a 3P subshell? Yes. Why is because okay, a subshell is made up of orbitals. So I want you to take note for electronic box diagram, right? Can I write this? One box represents one orbital. As I said, it's just a pictorial representation. A 3P subshell is made up of 3 orbitals. That one you might need to clarify a bit later again. Okay, 3 orbitals. So I need to see 3 boxes. Can you draw it on the side? Okay. How do we arrange the electrons? 3 electrons, how do we do it? Okay, they must be single first before you pair them up. As mentioned, it's like when you sit on a bus. Everyone wants to sit alone before you sit with other people. Guys, how do you draw 3P form? 1, 2, 1? Correct. 1, 2, 3, and then the 4th one. This guy, no choice, I have to sit beside the guy. Yes, we are upside down because electrons are they call it opposite spin. You don't even need to know what that means. Some physics term, right? Just one up, one down. Okay, guys, taking a look at this. Okay, so notice your boxes are separate, right? Okay, try to put the boxes together. That's faster that way. Yeah, I think most of the time your boxes should be together. It's just a pictorial representation, as you can see. Why are we drawing this out? Because I need you all to understand this one idea. Do electrons like sitting with each other? No. So guys, you can see clearly this guy's not very happy about it. What will happen? There's repulsions. If there's repulsions, means what? I'm trying to remove electrons. It's still ionization energy. Is it easier or harder to remove from this guy? Easier. He already wants to leave, right? So sure, he's willing to just go by himself. Less energy is needed. These guys here are much more happy. But how do you explain this? Okay, so I need you to think of words. For this second anomaly, it's called inter-electronic repulsion. It just means between electrons, there's repulsions. Okay, so you must specify first. Let's compare. The 3P subshell of sulfur contains a paired electron, which experiences inter-electronic repulsion. Now, why am I so particular on this? Because everyone remembers inter-electronic repulsion, and that's the first thing they write in the answer. But wrong. Because if you all realize, where's the inter-electronic repulsion? There's paired electrons here, 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 here. All these are paired electrons, but no, I'm only focused on the outside. Okay, I'm removing electrons from the outside. Compare 3P and 3P4. Okay, there's only paired electrons in 3P of sulfur. So it must be very specific. Where are the paired electrons? Where are the repulsions? Okay, so if there's repulsion, then obviously less energy is needed for removal. Oops, it's needed to remove the electron from sulfur. Okay, ionization energy is always must talk about energy. Okay. Okay, so that concludes this ionization energy anomalies portion. There are 2 dips, and you need to know these numbers. But why I'm a bit careful, cautious about this is because, guys, if they change this to second ionization energy, do you think it's going to be the same groups? No, it's going to shift. As for how it shifts, okay, let's not talk about it now. Later we'll discuss. Okay, so yes, you are removing from a different species, so everything shifts. Okay, a very brief idea is this. If I change this to second ionization, I don't want you all to memorize normally change it to 1. Okay, but how do we discuss the electronic configuration? Is it for this atom? What species do we need to draw the configuration for? Close enough. Okay, but what's the species first? Remember, for second IE, you look at which species? X with what charge? Plus. So that's why all these ones plus. In other words, you must remove 1 electron, so 3s2 becomes 3p1. This one becomes 3s2. Can you see that? Then now you're actually removing the second electron from both in the 3s. Are there any anomalies here? Are you going to see the 3s problem? No. So that's why you cannot stick to group 2 to 13 anymore. It will shift. It will shift to what? Maybe some of you guys can figure out. Is 13 and 14. Yeah, okay. Again, I don't need you all to memorize okay, what it shifts into. What's important is no matter what ID they give you, later we will see the tutorial. You just need to know which species you're looking at. Here's X plus. You see that? Okay, good. Okay, with that said, okay, we can turn over to page 30. Okay, we finish a set of notes first. Okay, left a little bit more on it, then we can take a break. Okay, so go over to page 30. Okay, you guys know what transition elements are like briefly, okay? Do you know where it is in the periodic table? Okay, you can just point out to me first. From which proton number to which proton number? 31 to? Okay, it's from 31 to 30. Okay, that's like the transition elements we learned in our syllabus in JC also. Okay, anything below that, okay, we won't have a touch. Okay, the definition of transition elements is in the notes, but I can safely say you are probably not going to be tested on this now. Because transition elements is the last topic of the entire syllabus, like late into J2, then you will learn. So this one not necessary now. Okay, you can write that at the side. Definition now don't need to study. Okay, again, it depends on what the school say also. They can choose to test, so that one must be what the school say. Okay, but yeah, no transition elements definition for now. But what we are interested in are the trends. Guys, when we go look at the transition elements, are we going down the group or across the period? Okay, yes, they even say across that, I just realized. Okay, so across the period means you still need to stick to the effective nuclear charge. So let's whip out the equation once again. So effective nuclear charge is nuclear charge minus shielding effect. Good. Okay. Again, when you go across the transition elements, what happens to the nuclear charge? Increases. Why? Protons increase. Okay, come, let's put it in. Okay, so across the transition elements, number of protons increase. So number of protons increase. So shielding, nuclear charge increases. Okay, so nuclear charge increases. And before we move on to the second point, I want you all to maybe at the side, right? Okay, you can write down the configurations for these species. Basically, some examples of transition elements. We're going across the period, so just take a look at this. Go and write down all 4 of these configurations. Yeah, at some point, the configuration will be repetitive. And there's a reason why I asked you all to write 4 down. Three. Yeah, write out 1 first. Okay, remember the rule first, right? You all notice, right? All these are 22 to 25 electrons. Beyond the 18, okay, so basically the first 18 electrons don't really matter. They are all the same. Okay, so we call the rules up. We must fill in 4s2, then 3D afterwards. 4s first, then 3D, like what we highlighted the last lesson. Okay? It's just that you need to write in ascending order in terms of quantum shell. 1, 2, 3, 4. Yeah. Okay, the first 18 kind of like repetitive, so I'm just going to do this for the next two. Go and check your answer. Okay, so remember chromium. Chromium was an exception. So there's a reason why I gave you this to just help you all remember. Other than chromium, there's another guy. Who is it? Also starts C. Copper. Okay, you all need to remember two of these exceptions. Okay, for both chromium and copper, you must put 4s1, then the remaining is 3. We explained it last lesson also. Okay, and for that's why when we go through the trend later, I will just have to ask you guys to ignore this exception and then move straight to manganese. So later, when we go across the period, you all look at 22, 23, then 25. Okay, then you will better help us explain. Okay, Ken, sorry, you okay? It is just an exception. Yeah. All right, next. If the number of protons increase, nuclear charge increase. Now, can we look at shielding effect? What happens to the shielding effect in this? Nope. Guys, shielding effect depends on the number of inner shell electrons. Can someone tell me what's the inner shell in this case? Okay, of course not 4s. 4s is the outer shell, 3D is the inner shell. Can you look up, ignore the anomaly. 3D, what happens to the number of electrons? It increases. Guys, as you have more and more inner shell electrons, what happens to your shielding effect? It can become stronger also. Your shielding effect increases. Your nuclear charge also increases. Come, let's write it down. Yes. So let's explain first. The shielding effect increases as electrons are added to the what? Are they added to the outer shell? No, it's added to the inner 3D subshell. Come, let's specify the full thing. That's why this one is different. Transition elements are you're adding to the inner 3D subshell instead. That's why shielding effect will increase. And as an overall effect, what happens to your effective nuclear charge? Yes, because it cancels out. So come look at the explanation here. You must kind of explain why it remains relatively constant. You don't say constant also. So it remains relatively constant. Then you can tell me because the increase in nuclear charge is cancelled out by the increase in shielding effect. So guys, that means what happens to the atomic radius? Also relatively constant. Okay, so that's the last point. Yeah, we're out of space. Okay, but yeah, okay, let me write it at the bottom here. Atomic radius. Relatively constant. Okay, so just be very, very careful. Never write it stays the same. Special case. Oh yeah. Okay, so special case in this context. Right? Okay, I ask you all write the configuration for practice also. You have to note the exception. Okay, so we can discuss page 31 also because it's nothing new. Because you notice, we always talk about atomic radius, then the next thing we talk about is ionization. And can you tell me, is the answer any different for ionization and everything? It isn't at all. Right, okay guys, for our transition elements, again, you're going across the period. Protons increase, nuclear charge increases, shielding effect also increase. So guys, what happens to the ionization energy? Also relatively constant. There's really nothing much for us to explain here. So guys, don't need to write it again. Okay, to save a bit of time, you guys can write there same explanation as page 30. So even though we are writing a lot of things down, again, a lot of it is recyclable. Okay, so you need to know how to study smart lah. Okay, don't go and look at every single box. Okay, must look at it from this perspective. Okay, same explanation. Okay, okay. Okay, so we kind of skip through this. Okay, and then we go to page 32. Okay, there is this one. Okay, 32 looks at some extra stuff. Okay, we're going to zoom in more into ionization energy. Right, okay, on page 32, we are discussing successive. What does successive mean? Okay, like one after another, continuous, yes. Okay, so what is successive, i.e. means you remove electrons one after another, right? First one you remove, second one you remove. Can see that? Okay, so when you do this, that means how? What are we supposed to explain here? Okay, guys, when you keep on removing electrons, do you think it gets easier or harder? Why? They start to get closer and closer to the nucleus because you're removing from the outside in, right? Okay, so you remove. Okay, but then right, it's not a full picture, like your logic is correct. But you all notice something. In a valence shell, for example, what if there's two electrons? After removing the first one, the second one is still equally far apart, right? But it still gets more neutral. As for Y, okay, look at the trend. Successive IE gets increases. There's no general trend, it just keeps on going up. There are two explanations. The first explanation, right, I don't think is very convincing. So later we'll write the second explanation. Okay, but this is still taught, so let's look at this first. We're going to use effective nuclear charge to explain the first reason. So guys, you think about it, as you remove more and more electrons, what happens to your nuclear charge? Nuclear charge is proton. No? Yeah, are you removing protons? No, okay. Okay, hold on. Okay, so your nuclear charge stays the same. How about your shielding effect, guys? As you remove more and more electrons, what happens to your shielding effect? It's decreasing, yes. Okay, this is where things get a little bit iffy. Because guys, you're removing electrons from the outside, right? But I did mention just now, shielding effect is for the shell electrons. That's why I say this is not very convincing. Okay, but it's still acceptable for some reason. Okay, what happens to your set effective? Yes, okay, it decreases. So let's write that down first. Okay, as electrons are removed, number of protons stay the same. Thus, nuclear charge stays the same. Okay, but your shielding effect does drop because you have less electrons, right? So shielding effect decreases as electrons are removed. I'm not a fan of this because clearly shielding effect is only dependent on your inner shell, but you're removing from the outer shell. So already there's a bit of an error. So I'll tell you guys about the second more convincing reason. Okay, but anyways, effective nuclear charge increases and so on. Okay, so as it increases, okay, there is a stronger attraction, right? You must tell me stronger attractions between valence electrons. Okay, so the energy needed will increase. Okay, not a fan of this. There is a shorter explanation which is a lot more convincing in my opinion. Okay, so we can take a look at the second version. And okay, so the preferred one, second one. Guys, if I were to ask you guys to write down the three equations, you can probably see a trend. Okay, give me your first, second, and third ionization energies. Okay, so x to x plus. Okay, plus to 2 plus. Yeah, okay, so you should know all these equations by now. Remember your gas state symbol. Again, it's just part of the definition. Again, who are we removing the electrons from? Which species? The left or the right? The left. Okay, so I always like to highlight the left so that we focus on this. Okay, guys, take a look. If you are removing electrons from those species, you notice how. Okay, hold on, you're right first. Okay, so look at the first one. What is holding the electrons back in the first place? What prevents the electrons from flying away by itself? Okay, the nucleus, right? You can see that. Okay, the nucleus in the atom holds the electrons in place. You need to overcome these attractions. That's why you need some sort of energy. But guys, you look at the next one. You're removing the next electron from X plus. Okay, not really about stability. You're removing this guy from a neutral species. Now you're removing electrons from a positively charged species. You all see it's harder to remove, to pluck out the electron, because a plus will attract the minus to a greater extent. And you look, the next one is X2 plus. Are the attractions here stronger or weaker? It gets even stronger. As you keep going and going, it's 3 plus, 4 plus, 5 plus, right? You are getting stronger and stronger positive charges. That positive charges will be so strong to the point where it will hold the electrons very, very back. So you need a lot of energy to overcome these stronger attractions. Can roughly see the idea first. We'll look at how to phrase the answer. Okay, so take a look. Over here, you can just say, okay, electrons are getting removed from an increasingly positively charged species. And you all can see it's just going to get stronger and stronger attractions. Okay, so let's continue here. Thus, the attractions between the nucleus and the valence electrons increases. Finally, talk about energy. So it's much faster. So the main driving point, right, is here. Remove from an increasingly positively charged species. I'll prefer this explanation because it makes a lot more sense. It's like getting more and more attractive as you remove more and more. Okay, and okay, almost kind of done with this. We are left with like 3 pages. Okay, can we look at page 33? This is an application of the successive ionization energies. Just by taking a look at this graph, you all already can see the energy needed just keeps on going higher and higher, right? But we can actually use this graph here to determine what this unknown element is. How? Okay, so you look at this graph here. Can I ask you, what is the first thing that captures your attention? Okay, good. The sharpest jump, right? That is the most striking feature of a graph. So let's mention that first. Okay, there's a very sharp jump from the 5th to the 6th electron. Guys, what does this mean though? Why does the 6th electron require so much more energy to remove? Is in the what shell? Is in the what quantum shell? Is inside. Okay, so you can see if the 6th electron is removed, it needs a lot more energy to remove. That means this electron is closer or further from the nucleus. Closer. See the inner quantum shell. Okay, think about it. Follow me through this. If the 6th electron is in the inner shell, that means how many were on the outer shell? And I'll see if we look at this. Yes, so it's 5. First electron removed, second electron removed, third, fourth, fifth. Then suddenly the 6th one is significantly harder because it's closer. You can see that? Okay, so with that said, our answer is very short. Number 1, you tell me the striking feature of the graph. There's a sharp increase in ionization energy. Okay, from the 5th to 6th electron. This implies, this means the 6th electron is inner shell. And don't just say inner shell, inner quantum shell. as we already know, quantum shell is really a huge jump in energy that I explained just now when I draw out the level diagram. So a huge jump in energy, that's why here also significantly huge jump. Okay, so hence there are 5 valence electrons. Hey guys, that means one group is in 15. This question says what group, but sometimes they can ask what element is it. So let's go ahead and answer this second question also. I know it's not said over there, but let's answer this. What group do you think this guy belongs to? Sorry, not group. What element? Okay, so group 15. Okay, what's the highest in group 15? Okay, nitrogen, then phosphorus, right? Okay. Let's compare these two. Nitrogen and phosphorus. Which one? Definitely not possible. Why?
There are more than 7.
Good. Okay, you see the graph? We already removed minimally 8 electrons, right? But nitrogen only has 7 electrons. So how are you going to remove the 8th electron, right? Okay, so nitrogen is definitely out. So if they were to ask you to give a possible answer, you cannot give me nitrogen at all. It must be minimally phosphorus. Okay, or you give me anything below that also okay. Okay, so that's the answer. Phosphorus is the likely element. Okay. Now I need you all to do the same thing, but for the next page. Page 34. Exact same thing, exact same explanation. 7. Oh, where are you minus? Perhaps I just convert with you. Okay, I should count this graph out. Okay, we shall now discuss this graph here. What is the striking feature you're supposed to look out for in this graph? Now there are a few sharp increases, right? Okay, but the main one should be 3 to 4. Why do we ignore this? I'll come to that. But then here should be between 3 and 4. Now I know some of you may be a little bit concerned with 1 to 2. Okay, eventually we will see why. Okay, we will ignore 11 to 12 for now. Later I'll explain why we ignore this. Again, our sole purpose is to identify the group And guys, how do you identify the group? It's based on the number of valence electrons. So that's kind of the reason why we ignore 11 and 12. Because valence electrons are removed first. Okay, so why not 1 and 2? Okay, because actually the bigger jump here should be 3 and 4. Okay, we'll come to that in a bit. Okay, I know this question maybe not very well set. Okay, there'll be a reason for that also. Okay, but we ignore 11 to 12 because we are concerned with the valence. Okay, inner shell electrons, we come to that later. Okay, so this question, maybe the graph not very well drawn. Okay, but in exam, don't worry, there won't be any. Okay, so let's just say 3 to 4, that's the biggest jump. So that means I let me modify my answer. The sharp increase from the third to the fourth electron. That means the fourth electron is in the inner quantum shell. Guys, how many valence does this guy have? 3 actually. The fourth is in the inside. So that means you have 3 on the outside. Make sense? Okay, so group 1. 13. Not 3, 13. Alright, okay. So what element is this? Okay, what's the first element in group 13? Okay, boron. Can it be boron? Okay, because boron only has like 5 electrons, right? But you can manage to remove 13 from this guy. So what's another answer? Aluminium. Okay, that's the answer here. Now we can annotate the graph a little bit more. Okay, let's understand every single thing in this graph. Okay, so I want you all to write down the configuration for aluminium first. Okay, 1s2, 2s2, 2p6, 3s2, 3p1, right? Okay, now you're removing the electron. Which electron you're removing first? Okay, 3p1. So guys, can you see this is the first electron? Let's label it as 3p1. Why is there a slightly sharp increase from 1 to 2? Okay, remember, different subshell got a slight increase. So 3s2, 3p1, we mentioned just now that 3p1 has a higher energy level. Okay, 3s2 will account for both of these guys, right? 2 and 3. After that, why is there a sharp increase? 3s. So the first initial jump is a subshell jump. But now, from 3 to 4, it is a quantum shell jump, which is a lot larger. So this is 2p6, and then you can count 8 very nice successive electrons, right? Okay, this one will be 2s2. Okay, but right, there should be a slightly sharper increase. Okay, that's why this graph a little bit outdated. Okay. And finally, why is there a very sharp jump here? Another quantum jump. So that's 1s2. Okay, guys, why do we ignore this? Because this one has no relevance to the valence information. Okay, there's really nothing there. It's inner shell. Why do we care about that? Right? Okay, you can see that for now. Good. Okay, there's another version at which we can test this question. So I just need you all to repeat the same thing for the next page. You should be no need to ignore the graph. Okay, the last page one, they can just give you numbers, but I'm sure this one's as easy. Okay, you gotta find where's the largest jump, can already. Hey, no need calculator. Are you taking a calculator? No need. Really don't need. You all can see the most obvious jump one. And then note it. No, guys, never mind. In exam, it will be super obvious like this. Yeah. Yeah, I mean, it's up to you. Oh my god, I need to go back to school. Oh, what's this? Me. From 10:30 to 4 p.m. That's too long. That's too long. But you guys are like from 7 to like 3, right? Is that normally school hours? Oh my god. No, like when your school start, let me see your timetable. I want to cry, man. I hate school so much. It's like I have a 3-hour lesson. 3 hours, by the way. That's ridiculous. So yeah, he is like legend. No, I don't understand. Why? You have no NS, you don't even need to like do anything. That's the NS life. My 3 hour lesson tomorrow. But this Indian guy he's like actually got Indian accent, so it's very difficult to hear. Yeah. A lot of them are like that. They are not local, so their accent is so thick, right? And it just hurts to hear. It's not like it's ugly or anything, it's just difficult. But I'm not gonna lie, there are some accents that sound better than the others.
So like, they don't exist was and my friends and I we found
Who's the guy next door?
on the RMS.
Oh,
And then they realized it was your why don't we use from the
oh, like just now. Sorry.
and just clean up like a shit. Now I'm going to the
Coincidence. You probably see more of your schoolmates coming here also. That's where most of our students are.
I was trying to figure out why you so familiar. Maybe some of them won't really.
Bring your friends here so to create a club.
I feel like
When your school hasn't even started, it's easy.
yeah. That remind me.
Maybe 16.
What's the condition for me? Yeah, me. Peace. Yeah, peace in the.
That's like everyone, right?
Oh, PCML. Oh, what's PCML? So your husband is a long hair, so. Nice. Oh, our first conversation, right? He was like, oh, my couple did it. I'm like, yeah, so the girl voice it. The girl said my other voice it.
Yeah, it's true. Yeah.
But your class will have more private girls.
If you take arts club, right, there'll be a lot of girls and like single digit number of guys.
Really?
There was a class in my school with 3 guys and like 20 girls. So it's oh, do not take arts. Please. Then the humanities program is a lot of gay people. Like the guys are very good. They are literally. Yeah, actually they like always touching themselves. Like no, each other. Then legit like all of them. I thought it was just a my bad thing. Then I asked the girl that seeing now, then after that she also said same thing. Yes, correct. And we're done with the notes. We can take a break right now. Later we do some tutorial questions to end off. Yes.
No.
Amazing. True person. Hey guys, for the last like half an hour, we are going to take a look at questions. Again, not the questions where you need to write like whatever we did in the notes, because those you can do yourself. Okay, just take a look at the first question. I'll guide you guys through a little bit. Okay. Oh, you got the tutorial. Yeah, okay, no, you all can read through first. I'm going to print over. The printer is like printing for like 20 people. Okay, so y'all might want to share first. Do you have the online version? Or okay, because I can send you the online version. Yeah. You are in the Google Drive, yeah, so you can access from there. Okay, I read through the question first, okay, then we will talk about easy way to solve this question. Yes. You go to notes, physical chemistry. Yeah. Eventually, this is going to get phased out because we bought the learning method, the LMS.
Which one, like?
No, notes, physical chemistry. Then atomic structure. Yep. Okay, so quite a few things happening here. Protons deflect by positive 15, but this unknown particle deflects by negative 5. Just based on this information alone, what can we deduce? Anything we can deduce here? It may not be electrons. Okay, now why do you say that? Okay, particle X is clearly not an electron because you look at the options for particle X. It's a lot of different stuff. Okay, protons deflect by positive 15. This guy deflect in the negative direction. So what does that imply? Okay, do they have the same charges? Okay, they have opposite charges, right? Okay, so protons are positively charged. So X must be negatively charged. That's why they deflect in opposite directions. Can you see that? Okay, so that's the first information we can use. We know X must be negatively charged. Okay, take a look at the options, right? Okay, because do you remember what's the angle of deflection formula? Or not formula, but the relationship? Okay, theta is proportional to Q over M. Now that's why we need to look at two factors, charge and mass. Okay, but the thing is here, okay, there's a lot of things going on. Can you all take a look at these four options? Can you all express these four options in terms of this format? What does that mean? I want to see the proton number, mass number, and then this is like A, B, C, D. Okay, and any charges if there are any charges. Okay, I want you all to write down the proton. Basically, I want you all to accumulate all the information. So proton number you put here, mass number you put on top. Yeah. So that's how you have a nicer looking thing to do the question. Okay, can, right? Let's look through the options. Proton number here is 1, 3. What's the charge? No, minus. You only have one extra electron over a proton. If they have same number of protons and electrons, then it's neutral. So you must look at the excess charges. How about the second one? B?
5, 2,
5, 2 minus. Then 6, 3 minus and 4, 9. 9, 4, 3 plus. Good. Okay. Weight X is what charge in? Protons positively charged deflect in the positive direction. Negatively charged then can deflect in the negative direction. Answer is not D. Yes. Okay. It's one of the three options A, B, C. Okay, but now we actually need to determine why it's 15 degrees and why it's 5 degrees. Okay, I can give you guys a bit of guidance here, then you can do it yourself. Okay, but to make this a bit easier, guys, for protons, can you express it in the same manner? Let's just say protons start at the P. Can you express it in the same format? Okay, what is it? Okay, how do you express protons in this format? How many protons are there in a proton? One, right? What's the neutron? What's the mass number? One. Okay, the charge variable is positive, so you don't have to write anything there. Okay, so I know, right, this is a subatomic particle, but you can also express it in this format. Okay, can? So guys, the second thing that I want you all to do also, okay, to help you guys out a little bit. You all see this formula here? Proportional to charge, inversely proportional to mass. Okay, can we sub in values into this? You all remember? Can we sub values straight into this relationship? No. Is this an equation? No. How do we convert this into an equation? How do we change this into an equal sign? Hey, you need to add the proportionality constant. So guys, use this to perform the calculations, because here you actually need to find the 15 and the 5 degrees. So that's why I tell you all use the K method instead. Q and M is only for comparing, which is not very optimal for this case. So I leave it to you. Okay, go and see which one is the answer. Yes, it's correct. Okay, just to see how you all do this method again, all right? How do we find the value of K? Must use which particle? Okay, P, because we know everything about P, right? So when we do it for a proton, the angle of deflection is 15, K is unknown, Q over M is 1, right? So from here we can see that K is equal to 15. We can use this for the others because they're all passing through the same field. Okay? And then you just repeat this, and then you will notice, okay, for the sake of the recording, okay, for A, the angle of deflection we don't know, but K is 15. What's the charge? -1, so it's just 1. What's the mass? 3. So this is 5 degrees. B, you do the same thing. 15 is over what? 2 over 5. So you get 6 degrees. This one, that one. Okay, 3 over 6, which is 7.5 degrees. You can calculate it for everything. Okay, why did I put a negative here? It's because you can put the charge as -1. Okay. Hold on, wait, no, I made a mistake here. No, what am I saying? Okay, wait, scrap these two. I bet. Okay. No, here should be 15 times 1 over 5. This one is also 15 times 1 over 6. As for y, it's because we have to look at the charge. Q stands for charge, and we are looking at this. You see that? Okay, my bad. That was wrong. I was looking at the proton number. No. We have to look at the overall charge. Because the electrons play a part as well. So this 1 over 5, this 1 over 6. Okay, then we can get our respective answers. That's 2.5, I think. Okay, then it's at 3 degrees. Sorry. Okay, you want to put a negative charge can, so -1, -1, -1. So all of them have negative charges. Okay, negative degrees, sorry. You can even calculate the fourth one. Okay, K is 15. The charge in this case is what? +3. Yeah, okay, you have to look at the overall charge. Okay, not the proton. I made a mistake just now. 3 over 9, which in this case is also 5 degrees, but positive 5 degrees. You can see that? Okay. Okay, calculate for everything. Right? Okay, with that said, turn over to question 2. We're gonna do this question. Okay, part A and part B is a definition thing. If you all don't know, never mind, because we went through this in the previous topic. I don't expect you guys to remember the definition, but I need you all to do part A minimally. Bromine is a halogen. Wait, oh, you don't have the data book, is it? Okay, so yeah. Oh. Right. No worries. Yeah. So, rise. Rise. You just made me hungry. Không mưa không bây giờ right after the bit. Okay, so guys, you must have 35 bromine, 35 protons for bromine. From there, how many electrons? Only 33, because minus 2. Okay, 33 electrons. Okay, now this is quite rare that is so many electrons in play. But just know the first 18 electrons are just like that. What's next? Okay, it should be 4s2 first, then 3d, 10. Up until this point, I have a total of 30 electrons. I need another 3 more electrons. Can? What? Okay, now, a lot of the times in our syllabus, we don't go beyond 30 electrons. So it's very difficult for you all to remember what's next. But it's actually possible to guess. After 4s is usually 1. Okay, you see all the after s is always p, right? So here 4p, 3. Okay, no, we only need 33 electrons. Okay. If they ask for 36 electrons, then 4p6. No, I was just about to say that, but I was like, okay, my God probably won't count with 79 electrons. Oh my God, okay, 79 is the number of protons and neutrons. Okay, electrons must be proton number, then you minus off the sorry? Oh, it starts from argon, so you put bracket argon, right? Okay, I think should be can as well. But I think if they want full configuration, they say full. Okay, so full must have everything. Yeah. Okay, I don't expect you guys to memorize the relative atomic mass concept yet. Okay, so let me just tell you guys what the formula is. Okay, this one, if you remember, is the very first lesson that we did. And relative atomic mass is a ratio. So you can express it in the fraction that we discussed also. So this answer is the mass of one atom of an element over 1/12 the mass of one atom of carbon 12. It's a very odd formula, but you just need to memorize this. You can express it in this manner. Okay. What's important is I mentioned to you guys there are like 4 definitions: relative isotopic, relative atomic, molecular, and formula mass. Out of all of them, relative isotopic mass doesn't have the word average inside. For good reason, because isotopes are not average, but they're just isotopes. But when you want to find the relative atomic mass, then yes, you need to find the weighted average of all the different isotopes on Earth. That's why the one got the word average and this one don't have. So just memorize this like maybe a week before the exam. Okay, can? What's important is I want you all to take a look at part C. Part C is the slightly interesting one with a bit of math involved. Right, okay, so read through it first. I can give you guys a bit of background. Okay, you all understand what's happening in part C? Let me preface it. Chlorine has 2 types. How about bromine? How many bromine isotopes are there? Also got 2 bromine isotopes, but guys, you all see the chances of them actually occurring are different. Chlorine 35 to 37, what's the odds? Okay, 3-1, or in other words, 75 to 25, right? So guys, how about bromine? Okay, equal proportions, and this will help us to calculate our relative abundance later. In this case, our relative abundance just means the odds of this happening. Let me just go through the first one, guys. I'm sure you can tell me what are the possible combinations to get 116 and 118. You can try that yourself. Okay, but perhaps what I'm more interested in is how do you find the odds of this happening, guys? To get 114 is 79 and 35, right? What's the odds of 79 bromine occurring? Yeah. There's a 50% chance of you finding 79 bromine on Earth, right? So half.
So it's half times 3/4.
Half times 3/4. Answer 3/8. I don't know whether you have the probability in secondary school, but probably have. Okay, but the recap. Guys, why don't you add the probabilities together? Why you times? Okay, you say cos math, right? Okay, so I also say cos math. Okay, but the idea is this, guys. When you multiply fractions, do they get bigger or smaller? They get smaller, right? When you add fractions together, they get bigger. Why does the probability get smaller? Because I need you all to realize you need both of these things specifically. So it's like, guys, you are striking the lottery twice versus striking the lottery once. Okay, you want to strike the lottery twice because the chances are lower. So if you want both stars to align, the probability has to be lower. You need to multiply probabilities together. Why I say that it's because of something that will happen later. Okay, so you're going to try the rest.
Yeah.
Right, it's just bad. You already have seen this in chemistry now. Okay, so this part here is just some creativity question now. Okay, some. Sorry, your first.
Is it possible for them to do more than one portion?
Yeah. Yes, that is yes, correct. That's good. Hey guys, okay. So for the recording sake, 116. There are 2 possibilities, right? What? Yes, you get 79, 37, or yes, both are answered. 81 and okay, good. So you all recognize that there are 2 possible combinations. Okay, guys, how do you calculate the relative abundance here? Okay, so 79 bromine is half, 37 is 1/4. Okay, so 1/8, good. Plus half also times 3/4 equals to half. Now guys, why do you all add the probabilities here? Because can you all see now we have more ways to get 116. More ways means higher chance you add probabilities together. Okay, good. It's more interesting, right? Okay, so guys, how about 118? Okay, what's the probability here? You can multiply, but there's another way one, right? A minus 1 minus everything. So it's 1. Okay, and go and calculate the same way. Okay, so questions like this, you can expose you all to more interesting question types. Okay, come, let's still move on. Okay, we're not going to write like long ass explanations. Okay, that's not the point. Okay, can you now flip over all the way to level up question 1? We're only going to try the first part because second part can be found from the notes, right? Level up question 1, part 1. Okay. You don't need to explain yet, that one we'll do together, but I want you all to sketch on the graph like what they asked for. Can you find? Level up question 1. So it's here. Yeah, right. NJC 2018 question. Okay, you all just need to sketch on the graph. You all know what's happening in your sketch first. Later, I will explain the answer, then you all can find out. Sorry? Yeah, no, you good. Okay, let's figure out the whole thing. Come on, so we drawing on the board all together. And Bill need. Okay, so the elements, two elements before magnesium are sodium and neon. Sorry. Later I will print the one copy. So, okay, let's review the answers. You have finished the thing already. So, first one, sodium has to be very specific, guys. It has to be lower than both magnesium and aluminium. Make sure it's not like higher than aluminium. Because aluminium is just a anomaly that we talked about just now, it just dips a little bit. Okay, but this has to be lowest. Okay. Okay, as for why this is the case, come let's very briefly explain. Because for 2 marks, you all don't have to explain the full thing about effective neutral charge. Okay, across the period, guys, what happens to ionization energy? Okay, good. First, ionization energy generally increases. Okay, good. You wrote the word generally also, because there are some dips. Since it generally increases, okay, that's why sodium is lower than magnesium. Okay, so first IE of sodium, it is lower than that of magnesium. You can just compare with magnesium. Then in the graph, you can just reflect the point very clearly that's lower than everything else. Okay. The other one is neon. Okay, that's where our second one comes in. It is very, very high, higher than everything so far. Okay, over here. Okay, so I think Olivia, you draw below, is it? Okay, it has to go much higher. What? Nothing to do with stability here. No. Okay, guys, you have to understand now we're removing the first electron only, right? You must ask yourself where you are removing the first electron from. What subshell are you removing it from? So, guys, you have to understand something. All these sodium all the way to sulfur is in what period? Period? No. Period 3. And then neon is you reset to period 2 again, right? So there has to be some sort of a patch over here. Perhaps you write down the electronic configuration, then you can see it. Neon is 10 electrons. You can just write sodium afterwards as well. By just writing out the configuration, you can probably see it already. You can write for magnesium also can. You can like proof a point. Yes. So you notice something. You all just look at the configuration and just tell me what's so special about neon compared to all the other period 3 elements? Where are you removing the electrons from? Which subshell? 2p. Guys, you're removing from the 2p shell, subshell, sorry. Whereas the rest you're removing from minimally the 3s or even further 3p already, right? What are we actually comparing? Is it a subshell? Okay, what are we actually comparing here? Okay, yes, correct. Okay, but you notice we are removing the electron for neon is from the inner, not inner subshell. If you're looking at the number here, the number represents the biggest thing, the quantum shell. Can you all see? Period 3 means you're removing the electrons from the third quantum shell. But for neon, because you're in period 2, you're removing it from the inner quantum shell. So this is a quantum shell thing, not a subshell thing. Okay, so how we explain this? Removal of the first electron from neon is in the inner quantum shell, which is much closer to the nucleus. Okay, so guys, if it's much closer to the nucleus, that means what? Thus, attractions between nucleus and valence electrons are much stronger. So what? Yes, okay, always go back to energy. It requires more energy to overcome. That's why it is way higher than everything else, because this guy is from 2s, where sorry, it's from the second quantum shell, the rest are from the third quantum shell, which requires a lot more energy. Okay, see you from there. Okay. Good. We try one final question that we can end off for today. Okay, so those are done. You can turn over to level up question 5. Okay, level up question 5 now, the Gunman High question. I only want you guys to do 2 things. Part 1 and part 2. Yes. Of A part 1 and A part 2. That's it. Oh no. Because it's split with A. So, okay, I'll draw the graph on the board also. Okay. That's the reason why we want to go through this question. Okay, right, okay, part 1 is something I expect you guys to get correct already. Okay, so how? Good. Okay, good. Okay, so we already mentioned that you must always go one smaller. Okay, that's for first question. Okay, for part 2, they ask to identify element n. The thing is, I did not ask you all to explain, but I want to explain with you guys also. I need you all to take it down. What is it? Okay, no, not Leon. Okay, the reason why this question is difficult is why? Why is it difficult? Because are we looking at first ionization energy? No, we are looking at third IE, and the moment they change it up, everything else just get jumbled up. But let's stick to our roots first. Okay, let's not get shaken by this. What is the main thing about this graph that we need to look at? I know they draw a bar graph, but I just have to change it to this. We have to look at the most striking feature, which may not be the sharpest increase, but here's the sharpest decrease. So look at N to O. Just pay attention to this. You are removing the third electron from every single one of these guys. Third electron. So what does it mean over here if there's a very sharp drop? Where is the third electron located at in O? It's so easy to remove the third electron. Why? Why is it so easy? Where is the third electron? Okay, remember just now we look at the sharpest increase. If let's say this is the 5th electron and this is the 6th electron, the sharp increase means the 6th electron is in the what? What did we do just now? Inner quantum shell. But now we're going the other way. If there's such a sharp drop is in the outer shell. Can you see that? Okay, so let's talk about this. You can talk about it in 2 ways. This one requires so much energy because the third electron is in the shell. Let's annotate first. Third electron is in the inner quantum shell for N. But for O, it should be in the what? Outer shell, right? is on the valence shell or the outer shell so that it is super easy to be both. Now, you can explain it both ways, but I actually prefer to explain in terms of N, because N is the one that we've been explaining just now. A lot of energy means is in the inner shell. So let's work it out together. Okay, so talk about the sharp drum first. There is a sharp drop in third ionization energy from N to O. So what does this mean? It means that the third electron is in the inner shell, inner quantum shell for N. So guys, then what's next? If the third electron is in the inner quantum shell, that means how many in the outer shell? Again, we're only interested in valence shell because it allows us to determine the group. So, wait up. Don't get phased by the tree over there. Okay, if you have the third electron in the inner shell, how many were on the outer shell? 2, exactly. So, hence, N has 2 valence electrons. If you have 2 valence electrons, you're in group 2, just 2. Okay, because valence electron 2 means group 2. Okay, magnesium. Can we determine the rest just from magnesium alone? Why? Yes, consecutive. So O is aluminium. As you know, aluminium, the third electron is in the valence shell. That means there are 3 valence electrons. Can see that? Okay, so I prefer to explain the top one. Okay, so it really depends on both works. Okay, so you can go all the way back. Magnesium, before that is sodium, neon, fluorine, oxygen. Okay, they did say it spans across 9 elements in periods 2 and 3. So you can see this fulfills that. Okay, because just now a lot of people will say group 2, why can't it be calcium? You try to put calcium here, and you try to fill in the rest consecutively, you'll realize you will never hit a period 2 element. So that's why calcium is wrong. That's how you determine. So third IE are very tricky. Any questions? Okay, if there are no questions, that's it for today. Okay, that's the end of atomic structure. Again, you can redo the questions that we've done today, and of course you can try the other questions yourself. So just as of today, we have completed 2 topics already. That's very good. Okay, then JC, when school actually starts, don't feel as stressed. Okay, so we will take a look at a new topic next week, chem bonding. You have heard of it before, but the notes are 60 pages. It will take me about 3 lessons to cover. So yeah, the next topic is super ultra important. Okay, I'll see you guys next week still. Right. Okay, so that's it.